This is the last video for our class, so we're going to wrap up chapter 11. And in the last video, we talked about radioactive isotopes. Now, some isotopes are stable indefinitely, but others are radioactive, like the ones we talked about, and they're going to continue to decay through some form of emission, whether that's alpha particle emission or beta particle emission. Now, that means that as time passes, less and less of the radioactive isotope will be present because, again, it's decaying over time. So the level of radioactivity will decrease as well. Now, an interesting and useful aspect of radioactive decay is what's called the half-life of the radioactive sample. So, for example, let's say we have 100, oops, let me grab my marker. Let's say we have 100 grams of a radioactive sample. There's going to be a certain amount of time that passes before we get to 50 grams of the sample, or half of the sample. Now, this particular sample takes 12.3 years to decay to half its original amount. And then it would take another 12.3 years to get to 25 grams of the sample, and so on and so forth. So every 12.3 years, we're going to decrease the sample amount by half. All right, so how can we calculate something like a half-life? So we can determine the amount of a radioactive isotope that remains after a certain number of half-lives by using the following expression. So the amount remaining of our radioactive sample is equal to the initial amount times 1/2 to the nth power, where n is the number of half-lives that have occurred. So you would already need to know the number of or what the half-life is, right? So in our last example, it was 12.3 years. Okay, now let's do an example problem. So let's say we have an isotope, fluorine-20, and its half-life is 11 seconds. So it only takes 11 seconds for us to lose half of our sample to radioactive decay. Now let's say the sample initially contains 5 grams. How much of our sample remains after 44 seconds? Okay, so again, our equation is the amount remaining equals the initial amount times 1/2 to the nth power, where n is the number of half-lives. So we need to figure out how many half-lives have gone by in 44 seconds. So it looks like we have a total of 44 seconds. And if we divide that by the half-life, which is 11 seconds, that should give us the number of half-lives. So it looks like this would be, let's see, 44 divided by 11 is 4. Oh, I was spelling the wrong thing. Let's see, half-lives. All right, so we know that n equals 4. So now let's just plug in the rest of our information. So the amount remaining after 4 half-lives is equal to the initial amount, which is 5 grams, times 1/2 to the 4th. Okay, so if we plug that into our calculators, you could also write this as 5 times 0.5 to the fourth. That works too. But let's see, my calculator gave me 0.3125 grams. So that's the amount that will be left over after those 4 half-lives, so after 44 seconds. Now, you don't necessarily need an equation to figure this out either. You could say, okay, I know that I started with 5 grams, and after 1 half-life, I should have half that amount. So that would be 2.5 grams. And then after a second half-life, so another 11 seconds, I would have 1.25 grams. And then after a third half-life, let's see, what's half of 1.25? I might need to plug that into my calculator. Let's see, that would give me 0.625 grams. And then if we divide that in half again, so a fourth time, we get 0.3125 grams. All right. So that's another way to figure out how much you would have left. You still have to figure out how many half-lives you have overall, but once you figure that out, you can just divide by a half each time. It takes a little bit longer, but it still works. So let's do another practice problem. This time we're looking at titanium 44, so Ti44. So the half-life of this isotope is 60 years. So it takes a really long time for this isotope to decay. Now let's say a sample initially contains 0.6 grams of titanium-44. How much of it will remain after 180 years? So see if you can do this problem on your own first, and then we'll go over it together. So you can pause the video. All right, so let's figure out how many half-lives we've gone through. So again, I'm going to take the amount of time that has passed, 180 years, and divide that by the half-life, which is 60 years. And that should tell me how many half-lives we've gone through. And this comes out to be 3, so 3 half-lives. So that means that titanium-44 has decreased by half 3 times. All right, so let's plug this into our equation. So the amount remaining is equal to the initial amount times 1/2 to the nth. So our initial amount was 0.6 grams, and our number of half-lives is 3. All right. So when I plugged that into my calculator, I got a value of 0.075 grams. All right. So there's still a little bit left of that isotope, so it's going to take a long time for that isotope to completely decay. So if you've ever seen the half-life of something listed, that's what it means. It means that over that amount of time, you're going to lose half of your sample. All right, so let's talk about some applications of radioactive isotopes. So one really useful application is what are called tracers. So a tracer is a substance that can be used to follow the pathway of a particular substance through some structure or some reaction. So down below we have the reaction for photosynthesis in plants. So carbon dioxide will react with water to produce sugar and oxygen. Now, one way that you can figure out the actual steps involved in this reaction is by replacing some of the carbon with carbon 14. So remember, carbon 12 is the most abundant isotope of carbon. Carbon 14 is very, very rare. It's present in a tiny, tiny amount. So if we use carbon 14 instead of carbon 12, we could try to follow carbon 14 throughout the reaction and see where it ends up. And that way we can figure out what actually happens during photosynthesis. So that's really, really cool that we can do that. Another application is for if we want to figure out how old something is. So for example, carbon 14, which has a really long half-life of 5,370 years, is really useful in determining the age of once living artifacts. So from an animal or a plant, for example. And that's because we do absorb carbon 14 from our atmosphere, even though it's very, very small in terms of its percentage. So once a living thing dies, it no longer absorbs carbon 14. So if we can figure out how much carbon 14 is in a sample, we can backtrack and figure out when was this living organism absorbing carbon 14. So we would use a similar equation to the one we used before, and we would try to figure out how many half-lives the item had been through. All right. Another application, we can use an isotope of iodine called iodine 131 to evaluate thyroid activity. So our thyroids are present kind of at the front of our necks, and thyroids are really useful in regulating our hormones and such. So if our thyroids aren't working, sometimes that can mess up, for example, our metabolism and our energy levels. So some people might have hypothyroidism, where their thyroid, again, isn't functioning properly. And typically, if you are hypothyroid, you're really tired and lethargic, and you can gain weight more easily. If you're hyperthyroid, then you actually tend to lose weight really quickly and at an alarming rate. So sometimes it's important to try to figure out what's going on in our thyroid. So the way that we do that is we administer iodine 131 to a patient, and the next day we use a scanner to measure the amount of radioactivity in the thyroid gland. And then the amount of radioactive iodine that collects in the thyroid is directly related to the activity of the thyroid. So that can allow physicians to diagnose the hypothyroidism or hypothyroidism. Now, luckily, iodine 131 has a pretty short half-life of about 8 days. So the potential for any damage from any radioactive decay is really, really minimal. And in fact, it's more important to try to figure out what's going on with the patient's thyroid so you can potentially save their life. And then off to the right, I actually have some scans of thyroids with the iodine 131. So you can see the thyroid almost looks like a little butterfly. All right, so those were some positive uses of radioactive decay. Of course, there are some cons to radioactive energy. Now, before we kind of talk about some of the cons, let's talk a little bit more about nuclear energy. So where does the energy come from? in our radioactive decay. So if we could precisely measure the masses of the reactants and products in a nuclear reaction, we would actually notice that the amount of mass drops slightly when we go from reactants to products. So in this reaction, for example, we typically round the mass of our isotope to a whole number, but the actual masses are listed below each isotope here. And if we compare the mass of the reactant, uranium, which is 235.0439, and let's say we add up all the masses of the products, we would get only 234.8605. So there's actually a little bit of mass lost. So we actually lost about 0.1834 grams. So where did it go? Where did this mass go? Well, it's typically released in the form of energy. And this is where Einstein's theory of relativity comes in. So you might have heard the famous equation E equals mc squared. So Einstein found that energy and mass are very closely related. So energy is equal to mass times the speed of light squared. And the speed of light is listed here, but it's not really important. We're not going to do any calculations here. But if we take that mass that we lost and plug it into this equation, so we plugged in the mass times the speed of light squared, we actually see that we lost about 1.65 times 10 to the 10th kilojoules of energy. So that is a huge amount of energy that's lost from a nuclear reaction. So each nuclear reaction is going to produce a ton of energy. Now, knowing that, scientists developed nuclear reactors because they thought, well, what if we harness that energy and we can just supply, our citizens with that energy? So we can run their cars, their homes, we can power the city using this energy. So in a nuclear reactor, this is something that's supposed to carefully control the progress of a nuclear reaction and then harness the resulting energy. So you can sort of see the layout here. We've got this nice thick wall around the outside, again, to try to contain any alpha particles, beta particles, etc. And essentially we have in the middle a reactor, and as the reaction's occurring, there's going to be a lot of energy that's released, and it's going to get very, very hot. So surrounding the reactor, we're going to place some water, because water has a really high specific heat capacity. So it can absorb a lot of heat. Now the water is going to be continuously pumped into the system and out of the system, because we don't want, any water turning into gas and then building up pressure from that gas. So we want to make sure we're getting rid of any hot water pretty immediately. Now, however, if a nuclear reactor fails for some reason, steam can build up in the reactor and eventually explode, right? It's going to cause an explosion. So that can be one downfall of a nuclear reactor. And in fact, that has happened, and we'll talk about that in a minute. But if a nuclear reactor is very carefully maintained and controlled, it can produce a lot of energy. So this map here shows the 30 most reliant countries on nuclear energy. So you can see at the top is France. France uses a lot of nuclear energy. And then that's followed by Ukraine, Slovakia, and Hungary. Beneath that, we have a few other, European countries there, as well as South Korea, let's see, Armenia, Belgium, etc. Now in green, you can see the United States is sort of far down on the list. We do have nuclear reactors, but in the 80s, we kind of lost faith on nuclear reactors, and we stopped developing them, and trust in nuclear reactors decreased. And we'll talk about why in a second. Russia's also pretty low down on the list here, Canada. And then you can see Japan doesn't really use a lot of nuclear energy, um, but we'll talk about one of its nuclear reactors in a second. So just kind of interesting how different countries utilize nuclear energy or not. So that brings us to nuclear disasters. This is partly why the US doesn't use nuclear energy as much as other countries. So if we start with 3 Mile Island, this was a nuclear power plant in Pennsylvania, and unfortunately, a nuclear accident occurred in 1979. And basically, what happened is a valve was mistakenly closed in the nuclear reactor, which shut off the water supply. And so the reactor was getting really, really hot. It did shut down, thankfully, but it was partially exposed because it didn't have water surrounding it. And this eventually led up to a buildup of hydrogen gas, and that caused an explosion. So after that, the US population did not trust nuclear reactors. And it's interesting because after that accident, there really wasn't too much that occurred afterwards in terms of radioactive exposure, but just the fact that it could happen scared a lot of people. Another famous incident was in Ukraine in 1986. Chernobyl was a nuclear power plant that exploded, and essentially someone was doing a routine test on the nuclear power plant, and something just went wrong, and excess steam from the reactor blasted the roof off and exposed the surrounding towns with radiation. And the people who were trying to shut down the reactors were exposed to a lot of radiation, which, if you're exposed to those alpha particles or beta particles, that can be really damaging to your internal organs. But additionally, the nuclear reactor was just really, really hot, which can also have negative consequences. So that was a really scary accident that also happened around the same time as 3 Mile Island. More recently, a plant in Japan, the Fukushima plant, had a disaster after a magnitude 9 earthquake. So that one was understandable, right? Now, that one was actually not so bad because everything shut down properly when the earthquake occurred. However, the backup cooling systems failed. So the reactors were just really hot, and there was a buildup of gas, and the roof exploded essentially. They did evacuate the surrounding area until they found that it was safe for everyone to return. And this was back in 2011. I remember when that happened, actually. It was pretty big news. That was, I think, the largest earthquake recorded in Japan. So there were really large tsunamis as a result of the earthquake, and it was kind of a scary time there. So again, this is sort of why trust in nuclear power plants has decreased over time. Um, but again, let's kind of go over some of the pros and cons of nuclear energy. So it is a clean energy source. It generates nearly 800 billion kilowatt hours of electricity each year, which is a lot. So it can produce more than half of our nation's emissions-free electricity. So this avoids more than 470 million metric tons of carbon each year, which is the equivalent of removing 100 million cars off of the road. But there is a high cost. Conventional reactor designs are actually multi-billion dollar projects. So, there's a trade-off there. And, if something goes wrong, it could be pretty scary for people living nearby. And there can be some pretty harmful effects like cancer and other effects. So, yeah, just sort of an interesting debate. Is it worth using that energy and having that energy, or are the costs too great? There's actually a really great show called Chernobyl on HBO if you have access to it. And I highly recommend checking it out. Although if you don't want to be too depressed, don't watch it. It's a little depressing. I think there's also another documentary that's out about 3 Mile Island. I don't know what network that's on, but yeah, there's usually documentaries about these nuclear accidents and disasters. So anyway, that is the end of chapter 11. If you have any questions, please feel free to reach out to me. But otherwise, I will see you at the final exam.